we have how much? Let me count first.
30, 30 I think.
That's okay.
30,
Around
30,
12 to
30
13
class.
class.
Oh, yeah.
They have different program.
Mm-mm.
The first program is accounting. The second is banking, and the third
Oh,
is
yeah.
business. The program they enroll in this subject STA 104.
Oh, yeah. Okay.
Doctor, how are you? Okay today?
Yes, Alhamdulillah, I'm okay.
Mm.
Here
Ah,
in Indonesia, today is a holiday because we have new Islamic year.
Awal Muharram.
Yeah, Muharram. Yeah.
Oh, yeah. We also public holiday today.
Oh, yeah. Yeah. I'm sorry
So,
because uh,
uh,
previously Dr. Afida offered me to give the lecture in Thursday, but I have two classes in Thursday, so I cannot, yeah, in charge
uh,
for the day. So yeah, I asked for Dr. Afida whether it is okay if we have lecture in this Friday.
in today, okay, it's okay.
Yeah.
Because
Okay.
I mentioned to all my students, so you have to come this today session.
I am sorry, really.
uh, so now because this public holiday and they are getting late juga, late juga.
Yeah. That's okay.
Okay, we wait for them 5 minutes more because before we start the session, but at
Okay.
least we have half of the student join this meet.
Yeah. Okay.
We call first our student.
That's okay,
Give us
doctor.
okay.
So, Dr. Nurliana and Dr. Shafiza, you are from what program?
Kak Syah first.
Okay, I'm Shafiza Saila, doctor. I'm not a doctorate yet. I'm teaching mathematics in your ITM Kedah. But then there's some semester that we need to cover for the statistics course.
Oh,
That's why
okay.
we need to teach the statistic.
Oh, yeah.
Uh, nice
Okay.
to meet you, doctor.
Nice to meet you, Dr. Shafiza.
I'm the same department with Madam Shafiza Saila, and I'm also teaching actually mathematics, my core. And
Mm.
this time, I have to give a lecture about the statistics. But it's
Oh, yeah.
interesting topic actually. And I have lectured this. I have take this subject about 2 or 3 sem already.
Oh, yeah. Yeah. Okay. Thank you very much for giving me opportunity to teach your students.
Doctor, before this, you already joined our correlative teaching also, right?
Yeah, in
Uh,
2023.
yes,
Yeah,
yes.
with Dr. Norin.
Dr. Noreen,
Yes,
okay.
yeah. This is my second time.
Second time. And
Yeah.
the same topic, right? The same topic.
Yes, the same
Same
topic.
topic. Okay, okay.
Mm.
So today we will see apa the topic that you cover. What the topic, the introduction of statistics, right? So what the subtopic? Until what topic? Subtopic.
Sorry?
The subtopic of the introduction to did you cover all the do we cover all the topic or certain topic subtopic in the
Oh,
topic 6 too?
do you mean
Do you cover all the topic, all the topic in the introduction to
oh,
statistics? We
yeah.
have topic, right? So do you cover
Yes.
all?
Yeah, actually I prepare all the topic for today's
Oh.
meeting, but let's just see the time for that.
Mm.
If we cannot finish the topic in this meeting, so I can just share my lecture note to you.
Oh,
And then, yeah, you can just continue from what I
yeah.
have prepared.
All right, okay.
That's good actually. Thank you so much, doctor.
Yeah, you're welcome.
Okay, we have another 3 minutes.
Assalamualaikum. Hi, Dr. Atina.
Waalaikumsalam. Hello, Dr. Afida.
How are
How are
you?
you? I'm okay, Alhamdulillah. How about you?
Okay, okay. Thank you.
Long
Thank
time
you.
no see, yeah.
Yeah, thank you for joining us.
I am the one who should thanks to you, Dr. Afida, for giving me another opportunity.
Okay. So what time is it now in Indonesia?
It's 9 a.m.
Oh, 9
Yeah,
a.m. So it's 1 hour
1 hour
earlier than us.
earlier. Yes.
So it's okay. Yeah. We're now in I'm in my place, in our place, Kedah. Today is a weekend. So we
Oh,
have a bit
yeah.
odd weekend. So it's Friday and Saturday is our weekend.
Oh, yeah. Your weekend is Friday and
Okay.
Saturday. Yeah. Here in Indonesia, because today is one Muharram, so we have holiday.
Oh yeah, yeah,
Yeah.
yeah. That's true. That's true.
So today is
Oh,
holiday. Yeah.
happy awam haram.
Happy one Muharram.
Happy New Year lah.
Yeah, New Year for us.
Yeah. Okay. Okay. All right. So I'll see you around. Okay. I'll be here, but switching off
Okay.
my video. My.
Yeah, that's okay.
Okay. All right. Thank you, Dr. Tina. See you.
Yeah, thank you. Dr. Nurliana. Uh,
Yes, Dada.
yeah, sorry. Can I try to share my slide first because I use another device here.
Yes, just please.
Yeah.
So you can apa try editing the sound and all.
Okay. Yeah.
Okay.
Yeah. Okay. Hmm.
Dr. Tina, are you there? Are you here?
Yes, yeah. Sorry, I still prepare my slide.
Oh, prepare. Doctor, let us know if you are ready to start the session.
Yeah, yeah.
Are you ready?
Yes,
Oh,
I'm ready. We can start.
okay, we start lah. Alright. Okay, so before we start, let us introduce to you. So first of all, Assalamualaikum and very good morning to all the student here. Okay, UiTM Kedah, and our invited speaker from which is Dr. Atina Andika from Faculty of Mathematics and Natural Science, Universitas Islam Indonesia. So today we have a collaborative teaching for STA 104. The topics we selected is Introduction to Statistics. So make sure student here, okay, pay attention to Dr. Atina because this is one of the topic for your assessment, right? So take this chance to know lot of information. Okay, learn everything. Okay, if you have question, you can write your message in the chat box, and I will read the question to Dr. Atina lah. Alright, clear everyone, student? Any response, please? Okay, saya nampak beberapa student saya. Okay, right. Okay, so without further ado, let us welcome Dr. Atina to start the session for today collaborative teaching.
Okay, yeah. Thank you very much, Dr. Nurliana. Hi, everyone. Assalamualaikum warahmatullahi wabarakatuh. Yeah, first of all, let me introduce myself. So I am Atina Ahdika. Actually Ahdika, not Andika, doctor. And you can call me Atina. Yeah, I should thanks first to Dr. Nurliana, Dr. Afida, Dr. Shafiza, and UITM for this opportunity because I think this is my first time teach in UITM, and it is a great opportunity for me. And now I am a lecturer in the statistics study program, and uh, as the head of the undergraduate program of statistics. Okay, then let me share my slides. Okay. Oh, I'm sorry, I need to try. Okay, so can you see my slides here, everyone? It is clear? Is it clear, everyone? I'm sorry, I am not really familiar using Google Meet because I usually use a Zoom meeting, and now I cannot see everyone because of this entire slide here.
But they are responding well with a good expression. Okay,
Oh,
all right.
okay, yeah, sorry. So it is clear, right?
Do
My
you
slides here.
right now you are not sharing yet lah, but I
Oh,
can see
not
your
sharing.
entire screen. You are presenting, but then you can
Oh,
you didn't you have to share. You already share, but you did open the slide first. You can buka slide.
okay, okay. I'm sorry. I have I rather confused using this. Okay, so I can try to use this one. I'm sorry here. Windows. How about now?
Yes, this
Is
is
it
very
clear?
clear, Doctor. We can see the
Oh,
slide
okay.
already.
Okay, yeah, thank you. Okay, so today I will give some let's discuss some matter regarding the probability, everyone here. So if can I know in what semester the students here, Dr. Nurliana? In
The
what semester, actually?
currently
Most of them actually in semester two.
Oh,
they are
semester two. Okay.
Semester two.
part to
Yeah.
semester
Okay.
two.
Yeah. So that's quite the same with our. Okay. So that's quite the same with my university, that
Uh-uh.
this subject is given to the student at semester two. Okay. Yeah. So thank you very much, and let's just start what we can discuss today. Yeah. Before we start our lecture today, I want to ask everyone here. I have this question. So, what is the minimum number of people in a room so that the probability of at least two people having the same birthday is more than 50%? Can anyone, uh, do anyone has idea for this? I want to know. Just guess. Everyone here, can you give me an answer? Four? Okay. Four. Other answer maybe? Three? Okay. So we only need four or three people to get the probability that at least two people having the same birthday. I rather amazed with the answer because um, usually people will answer that we need many or large number of people so that we have the probability that at least two people having the same birthday for more than 50%. Okay, that's a good answer. Muhammad Adib Iqbal, 23. Okay, so before we go to the answer for this question, I want to know the reason for these three answer. First, let me ask Muhammad Akil Aimal. Can you show yourself, Muhammad Akil? Hello, Muhammad Akil. Can you give us your reason why do you have four as your answer?
Because when there is four people in the room, uh,
Yeah.
the uh, there will be a probability of more than 50% of people having the same birthday.
Yeah. So how you get 50%, more than 50% for these four people?
Um, because in a room of four,
Yeah.
when for example, because when there's a room of four, um, room of four, uh, there will be at least 50% of people having the same birthday.
So you mean you just calculate two over four people to get 50%?
Yeah.
Okay, but yeah, thank you for your answer, Muhammad Akil. But what uh, the meaning of this question is that because you know that um, in 1 year we have 365 days. So the question is, we want to know how many people in a room, so that at least the people having the same birthday. Same birthday means the same day uh, of uh, of these 365 days. So I think for now it's not a right answer. But thank you very much, Muhammad Akil, for your answer. How about Putri Nurjeha? Putri, can you raise your sound? Putri, are you here? No response. So I want to go to. Oh, cannot open your mic. Okay. Okay, then the next, Muhammad Adib. Can you explain to us how you can get this answer, 23? Hello, Muhammad Adib. Okay. Yeah, if you cannot turn on your mic, so yeah, let's just continue. And your answer is right, actually. So actually, we only need 23%. We can say this as only because we have so many combination or so many possibilities that actually maybe intuitively we need many numbers of people to get at least two people having the same birthday. But the question for this answer will be discussed in our next what is it, in our next discussion. So before we discuss about how to get this number, so I will introduce to you some about the probability properties, so that we can answer this kind of question. So actually, we need the information, or we need the knowledge about the probability before to get the information about or the concept of the probability. We also need the other properties for this. For example, the first one, we need to know about the set theory, and then after that we need to learn about the probability concept, and then the counting rules and something like that, so that we can answer this kind of question. So I think this is only for the introduction to this subject. What can I say? So that why do we need to learn about the probability? Okay, so I will continue to the next slide. Here, it is an interesting series. So I usually recommend to my student to see this series, because in this series you can learn many things or many cases about the probability. So the series title is Liar Game. It is a quite old series from Japan, but if you interest in learning about the probability, so it is a good movie to watch. Yeah, just try to look for this series. Okay, now let's talk about some term in the probability concept. But we will start this from the set theory. So we have some terms in the set theory that we should know and we should understand, so that we can define random variables before we calculate the probability. Okay, some terms of the set theory that we need to understand is, the first one is about the experiment. So experiment is a process that when performed, produce random possible outcomes. So, for example, if we have activity or we have process like tossing a coin, we know that from tossing a coin, it will produce random outcomes like the appearance of head and the appearance of tail, or when we tossing a die, so we know that we will produce random outcomes for appearing 1, 2, 3, up to 6, or other experiments. So the experiment itself is a process or activity that produce a possible random outcomes. Uh, this means that we cannot drive the outcome to be something like what we want. That's called experiment. The second one is the set or collection of all outcomes from the experiment is called as sample space. So for example, when we toss a coin and the outcomes will be like a head and tail, so the sample space that is usually denoted by big S is a collection of these outcomes. So we have S, the member of S is head and tail from tossing a coin. If we have the experiment that is tossing a die, so the sample space or the member of the sample space is the outcome of 1, 2, 3, 4, 5, and 6. And then for the other example is, let's say we have an experiment of, for example, a driver, an online driver. Uh, he drive and will cross 3 intersection, let's say, and in each intersection they will have face a traffic light, and then in each traffic light he can be stopped or he can just go through. So for this kind of process or activity, we can also call this as experiment, because this driver cannot set or cannot, what is it? They cannot, the outcome or the result in each intersection cannot be driven by this driver. So when this driver get like red or yellow yellow light, so we can say that he will be stopped. Or when he get the green light, so he will just go through. So, because in each intersection, he will get 2 possible outcomes and he will go through or go past 3 intersection. So, the outcome or the member of the sample space for this event is how many, do you think? How many member of this sample space? So, a driver go to 3 intersection, and in each intersection, he will face a traffic light, and for each this intersection he will stop or he will just uh, go through this intersection. So in this event, in each intersection we have 2 kind of possible outcomes, that is stop or just go through. And then because we have 3 intersection, so we will have 2 power 3 member for the sample space. Actually, I need to write, but let me try to use my device first. Can I just write using this? Okay, sorry. I have one solution for this. I don't know. My PDF slide is rather bad to be used for my slides. So I'm sorry. I need 1 minute to join through my iPad. I'm sorry, Dr. Nurliana. Give me time.
Oh, yeah, it's okay, doctor. Take your time.
Yeah. Mm. Okay, let me try and use another device. So, okay. Let me stop this slide first, Doctor.
Yes, please, doctor.
Sorry.
Okay,
Yeah,
tak apa. It's
okay.
okay.
And then nah, I think it will be better.
Yes, very clear. Okay.
Okay. Yeah, so yeah, I'm sorry. So I will go back to our discussion before. Sample space is the set or collection of all outcomes from the experiment. So, for example, we have, let's say, we have an experiment. Experiment is not only like a tossing coin or tossing die. So, for example, if we have like what I explained to you before, let's say we have a driver that will cross into three intersections, and in each intersection he can stop or just go through. So uh, there is two outcomes in each intersection, but because we have three intersections, so the possible outcomes for this is 2 power 3, or we have 8 possible outcomes for this. For example, let's say that we have, we have S here. Okay, let's say we have S here, S stop, yeah, or P here as pass the intersection. Okay, now in the first intersection, let me use maybe this slide. Okay, so we have three intersection. The first intersection, let's say here I have intersection 1, and then intersection 2, and then intersection 3. In the first intersection, he can stop or he can pass the traffic light. And then in the second intersection, he can also stop or pass. But we should pay attention to the first intersection. If in the first intersection he stopped, then in the second intersection, he will get a possible answer to stop or pass. Again, uh, even if he passed in the first intersection, so in the second intersection, he can also stop or pass. And again, in the third intersection, this is third intersection. So in the third intersection, there will also be possible outcome to stop or pass. Here also stop, pass, and stop, pass. So we have 8 member for our sample space here. So our sample space here will be stop, 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 pass, and then stop, pass, stop, and then stop, pass, pass, then pass, stop, stop, pass, stop, pass, and then pass, pass, stop. and pass. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 members of sample space. So we can also say this as an experiment because this experiment produced in the possible random outcomes. Okay, so this is the other example for experiment, and its correspond sample space. And then we have also another term for this that is called as event. So event is a collection of one or more outcomes of an experiment. So this event is also a subset of sample space. For example, here, if we have this kind of sample space for our case, so we can define an event that is a subset of the sample space. For example, I will define A, event A, as the at least at least 2 stops for the driver. So what do you think the member of A? At least 2 stops for the
Should be more
driver.
than two.
Yeah, yeah, Hairani. Can you list the member of event A? We define an event, let's say as event A, and this event represents that at least 2 stops for the driver. So what do you think the member of this event A?
Four.
4? What is it? What is it for this 4 member? 4 members, right? But what is it?
SSS,
Okay.
SSP, SPS, PSS.
Yeah, yes. So we have SSS, SSP, SPS, and PSS. Yes. So because this the member of A is the subset for our sample space, so we can say that A is an event. Yeah, so that's the definition of event. Okay, I will go to the next. Also, here is the example for experiment, sample space, and event. So for example, here, yeah, we can say this as a common example in the introduction to probability. The first example for experiment is, yeah, toss a coin once. For one time tossing coin, so we have only 2 possible outcomes. That is the appearance of head or tail. So our sample space here is H and T. And then we can define our event. Yeah, because this is only one time tossing coin. So of course the event, yeah, just we have limited definition for our event here. For example, here the event here is the appearance of the head. So we have the member of A is only H. Okay, and then the other example for experiment is roll a die once. When we roll a die once, so we can get the outcomes is the appearance of side 1, 2, 3, 4, 5, and 6. And then we can define an event from this sample space. For example, the appearance of the event number. So the member of this event is 2, 4, and 6. The other event is that we can, the complement for B. So we can define an event that represent the appearance of the odd numbers. So the member for this event is 1, 3, and 5. Can you also give me another event for rolling a die once? Anyone? Give me a number example, another example of events other than appearance of even number or odd numbers. Anyone can give me another example of events? Can I just call your name? Maybe Amirah Damia. Amirah Damia, can you give another example of event from the experiment of rolling a die once? Hello, Amirah Damia. So, other volunteers maybe? What is it? Okay, then let me give you another example. Okay, for example, we have B1, let's say. B1 is, let's say, the appearance of the die side that is less than, let's say, less than 3. So what are the member for B1?
1 to 3. I'm so scared.
Yeah, less than 3. So 1 to 3 or only 1 and 2?
Less than 3 should be 1 to 3, right?
Okay, we usually use the term like less than or equal to 3. Then 3 will be included.
Oh,
Yeah, but
okay,
if
I'm
we
sorry,
use,
doctor.
that's okay. That's a good answer. Thank you, Hairani. So if we use the term of less than, then 3 is not included. So we have 1 and 2 here. Yeah, okay. Okay, so that's the other events that we can define. Okay, so let's see for the other example of experiment. Toss a coin twice. Yeah, because we toss a coin twice, where each coin result in only two possible outcomes, that is head and tail. So just like before, we can use like a tree diagram. We set this as tree diagram. So in our first outcome, we have H and T, or head and tail. And then in our second outcomes, or second tossing, we can also get H and 3. Also, we can also get H and T. So here we should pay attention on the first tossing and the second tossing. So that if we toss a coin twice, we will get the outcomes is HH, HT. So our sample space here is HH and then HT. And then if we get T in our first tossing, so we can get TH and TT. So this is our sample space. Okay, then we can have the event of this sample space. For example, here is event C. So C here, the member of C here is HH, HT, and TH. Now the question is, if the member of C is like this, so can you define this event? So what event is explained through this member? If we have this kind of event, so what do you think the definition of this event?
At least one head.
Yes, yeah, true. Thank you, Hairani. So we have an event that at least one head appear. in the tossing of a coin twice. Yeah, good. Thank you very much, Hairani. Okay, so this is we still have another common examples for experiment. So like play lottery, we have win and lose as our outcomes, and then select a worker based on their gender. So the outcome will be male or female. So this is the examples for experiment, sample space, and event. Okay, now we will talk about the properties of the event. Sorry. Okay, so we will talk about the properties of events. Now, previously we talked about an event defined from a sample space. So now consider we have two or more events. Using these two or more events defined on our sample space, we can have the relation between these two or more events. For example, the first one is the union of events. So the union of events means that we combine all the members of these two events, but mathematically written, we only write the member of the union or the combination of these two events only once. Okay, we will see the example next. The first one I should explain to you what is the definition of the union of events. Okay, so suppose we have two events, for example, A and B, that are the subset of the sample space S, and then we can define a new event called as union of events. We have the notation here. So just like a cup, this cup means the union between A and B. So the union between A and B consists of outcomes that are either in A or in B or both in A and B. If we represent this relationship between two events using the Venn diagram, so we can have this kind of graphic. Yeah, so we combine or we unify the member of A and B. So the equation 1 here means that, let's say we have C as a new name of this new event. So let's say C is the union between A and B. Then when we take, oh sorry, okay, sorry. Yeah. So let's say we have a new name for this new event. Let's call that as C. C is the union between A and B. So if we take a member from the C randomly, so for example, I will take little a as the member of C randomly. So this A can be a member of big A, or it can also be a member of B, or it can also be the member of both A and B. So this is the formal definition of the union. Okay, now I will give you the example. For example, we roll a die once, and then we define the event A as, let's say, the appearance of the odd numbers. So the member of A will be 1, 3, and 5. And then let's say we define B as the appearance of the numbers that is less than 3. So here we have the member of B is 1 and 2. And then we will make a new event here as the union between A and B. So here, if we look at the member of A and B, and we unify these two events, so the member of the union between A and B will be 1, 2, 3, and 5. Yeah, and the mathematical definition of the first equation here means that if we take a member randomly from A union B, for example, we take our little a here is 2, let's say. So this number 2 can be the member of A, or it can also be the member of B, or it can be the member of both A and B. In this case, 2 is the member of B. So the term or here can be one of A or B. So no need to be in A and in B. Differentiate between or and N. So differentiate between term or and N. Or means that it can only one of these two, but N means that it should be in the two events. So for the term N, we have the intersection of event here. In the Venn diagram, here we can see that A intersect with B, or the notation is like this, just like a cup, but in what is it? In the converse position. So we have here A intersect B. Here means that if we take a member of A intersect B randomly, let's say a little a, so A should be a member of A, and this little a also should be the member of B. So if we draw that in the Venn diagram, this A should be here. Yes, so this is the representation of the intersection between events A and B. Again, we have the example as before. So A is 1, 3, and 5. And then B is 1 and 2. So the intersection between A and B will be, what is the intersection between A and B? The member that is the member of A and also the member of B.
One.
1, yes.
One.
Yes, okay. So the member of A intersection B is 1. Okay, let me give you another example. For example, we have A as the appearance of the odd numbers, and then I have B1 as the appearance of the even number. So we have 2, 4, and 6. So if the question is what, I'm sorry. Okay. If the question is what is the intersection between A and B1, so the answer is, what is the answer for this? What is the intersection between A and B? Is there any intersection? Do we have intersection between A and B1?
No.
No, yes, we don't have an intersection for that. So if we don't have intersection for that, we will use this notation. This. So this is empty set. This called as empty set, or we can also use this notation. Yeah, this is also called as empty set. So if there is no intersection, then we can use this notation, and we call this as empty set. Okay, that's the second properties of events. And then the next one is mutually exclusive between events. So like the previous example, if we have two events and there is no intersection between these two events, then we say that these two events is mutually exclusive. So there is no intersection between A and B here. So we can say that A and B1 here is mutually exclusive. Okay. Yeah. Now, the complement of event. So the complement of event usually denote by this one. So a uh, a power c or a apostrophe, and then this refer to the complement of a. So what is the meaning of complement? So complement of a means that if we take any member of the of our sample space, then this member is the member of sample space, but it is not the member of A. So we write this. We write that sentence in the mathematical form as this. So if we have an event that is the complement of A, and then we take any, what is it? We take any member of A complement. We take any member of A complement. This means that A is the member of sample space, but A is not the member of A. So if we represent it in the Venn diagram, the shadowed area here is this one is the member of a complement of A. Okay, let me give you example. So for example, again, we will use A as the appearance of the even numbers. So we have 2, 4, and 6. So the complement of A should be, what is the member of complement of A? So the member of complement of A should be the other members in this sample space, but it is not the member of A. So for rolling a die only once, then the complement for A should be, what is the member of the complement of A here?
1,
3,
3,
5.
5.
Yes, 1, 3, and 5. Okay. Yeah, so that's the complement. Yeah, I think this should be only review because maybe about the set theory should be given at senior high school maybe. Yeah, but this one maybe is the, what is it? Is the development of some properties for events. Okay, so the next one is the partition of sample space. Let's say we have a set of event A1, A2, A3, etc. And this set is said to be a partition of sample space is if this set meets two requirements. The first requirement is that all the events are mutually exclusive, means that there is no intersection between each of this event. And the second requirement is that the union of all of these events should form a sample space. Yeah, geometrically drawn, the partition should be like this. So we have no intersection between event, and the union of all of these events should form a sample space. For example, let's say we, okay, let's say we roll a die twice. So how many members of the sample space of rolling a die twice? If we roll a die twice, so how many members do you think for our sample space?
12.
12? Other answers, maybe?
36. Maybe.
36.
I'm just guessing.
Yeah. Yeah, so if we roll a die twice, yeah, that's right. The members of our sample space is 36. So 36 means the pair, the member means the pair of the first rolling and the second rolling. So here, because in the first rolling we have 6 outcomes, and in the second rolling we have also 6 outcomes, and each number will be paired with 6 uh, 6 next outcomes. So if we have 6 outcomes, we will have 6 times 6. So we have 36 outcomes for rolling a die twice. So here, let's say our sample space here is 1, 1, and then 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And then we have also 2, 1, 2, 2, 2, 3, 2, 4, extra. I will just write this like this. So 6, 1, 6, 2, until 6, 6. Yeah. So here is our sample space. Okay. Now, let's say I have 6 events. Let's say I have 6 events. So we have A1, A2, A3, A4, A5, and A6. And each of these events defines the appearance of, let's say for A1, is the appearance of side 1 at the first rolling. So the first row will be A1. This will be A1. And then let's say A2 is the outcome of rolling a die twice where 2 is in the first outcome. So this will be A2 extra up to A6. If we see here, the member between A1, A2, A3, A4, A5, and A6, there is no intersection between each of these events. And then also, if we unify all of these events, that will form a sample space. So we can say that A1, A2, A3, A4, A5, and A6 is a partition of sample space. So this is the example of the partition of sample space. I will give you the example of a set that we cannot say that as a partition. But I think for this rolling die twice, rather we have rather large member for this. So I will simplify this example here. Let's say, let me erase this first. So let's say we only roll a die once. Okay. Let's say we only roll a die once. So our sample space here will be only 1, 2, 3, 4, 5, and 6. Okay. And then let me define A1 as the appearance of the side that is less than 3. So we have A1 as 1, 2. And then let's say A2 is the appearance of the side of die that is an even number. So we have 2, 4, 6. And then at 3, let's say the number of the appearance of the die that is, let's say, 3 or more. So we have 3, 4, 5, 6. Okay. And then can we say that A1, A2, and A3 is a set of partition of sample space? So A1, A2 and A3 here, is it a partition of sample space?
I think yeah,
Yeah, why?
but I'm not sure because um A1 doesn't have members of 6. So we cannot assume that as I don't know how to explain, but I think my answer is no. Yeah. It's a part of partition of sample space.
So your answer is these three events is a set of partition of sample space. That's your answer, or not a
Yeah.
partition?
But I'm sorry if I'm wrong. I don't know. Yeah.
Yeah, okay. So let's see here, because a set of events can be said to be the partition of sample space should be met these two requirements. So we should check. Okay, the first one, let's see. For the first requirement here, let's see. Is there an intersection between A1 and A2? Is there
Two.
any intersection between A1 and A2? Yes, we have intersection for that. That is 2. So the first requirement is not met here because we need to have the mutually exclusive events in the first requirement. So because this intersection between A1 and A2, also if we see here, A2 and A3 also, we have intersection for that is 4 and 6. So even after we unify all of these event, it will form a sample space that is 1, 2, 3, 4, 5, and 6. But the first requirement is not met by our events here, so we cannot say that the set of these events here is a partition of sample space. So this is not a partition of sample space because
Oh.
it doesn't meet the first requirement. Although the second requirement is met. So we should meet these two requirements. So that's the answer. Again, I will give you another example here. For example, I have B1 that is 1, let's say 2, 3. And then B2 is 4. And B3 is 6. So let's see here. Between B1 and B2, we don't have an intersection. Also, between B2 and B3, we also don't have any intersection. And between B1 and B3, there is no intersection also. So the first requirement is met. But the second requirement here is not met. Because if we unify B1, B2, and B3, this will result on 1, 2, 3, 4, and 6. So there is no 5 here. So it doesn't form a sample space. So we cannot say this as a partition of sample space. So we can say the set of the event to be the partition of sample space only if these two requirements are met. But if we only meet the first requirement or only the second requirement, so we cannot say that our set of event is the partition of sample space. Yeah, so that's the other property of event. Okay, here I have example. Yeah, so consider the experiment of tossing a coin 3 times with a sample space like this, because we have 2 outcomes for each tossing, and then we have 3 tossing, so we have 2 power 3 member for our sample space here. So we have 8 outcomes. And then Let A be the event that at least two tail appear, and B be the event that one head appears. So here we have our member of the event A and B is just like this. So because the event A is the event that at least two tail, so we should gather all of the members that has at least two tails. And then for B, the event that one head appears, so we have this member. So my question is, the first, what is the union between A and B? The question is, what is the union between A and B? So can you just uh, list the member of the union between A and B? Or
H T
maybe my first question is, how many members for the union between A and B? First, before we list the member. So how many members?
4
Four, yes. Well, what is it?
HTT
Yes,
THT
HTT.
TTH, and the last one should be TTT.
Yes, yeah. So we unify the member of A and B. And again, I say to you that if we have same member between A and B, then we only need to write that once. So for example, here we have HTT, THT, and TTH. Each of this member is in A and B. So we only need to write that once. So the member of the union between A and B is 4. Okay, thank you. And then the second question is, what is the intersection between A and B here?
3
Yes, what are they?
HTT
HTT,
THT, and then the last one
THT.
TTH.
Yes, TTH. Yes. So the intersection is the member that is on A and also on B. Okay. Then the next question is, are A and B the partition of sample space? Are these
Sorry,
two
doctor.
events, yeah, are these two events is a partition, are these two event a partition of sample space? Can we say
No.
that as a yes, okay. No, because the first one we have intersection between A and B, so the first requirement is not met. And then the second one, the union between A and B doesn't form a sample space. So the two requirements are not met. So we cannot say that this is as a partition of sample space. Okay, yeah. Here also we have information that A and B are not mutually exclusive, of course, because we have intersection between A and B. Two events can be said to be mutually exclusive if there is no intersection. But because we have intersection here, so we can say that there is these two events are not mutually exclusive. Okay, then if the question is, what is the complement? Here is the complement of A. So my question is, what is the complement of B? So what is the complement of B? Because we have HTT, HTT here is this, and then THT here, and then TTH here. So the complement of B should be HHH, HHT, HTH, THH, and TTT. Yeah. So the complement should be the member of the sample space, but not the member of B. Okay. Yeah. Okay. Here is another example. Suppose we have an experiment of tossing a die, and we have the set of events like this. The first set is just like this. So A1 consists of 1 and 2, and then A2, 3 and 6, and A3, 4 and 5. And then we also have like this, B1, B2, B3, and B4, and then C1, C2, and C3. Which event set do you think the partition of sample space? Which one? Which one is the partition of sample space between these three sets?
None.
No. How about others? Maybe the other have a different answer with Airani?
Set one.
Set one. Okay, yeah, thank you, Nur Farisha. So yeah, the right answer is set one. If we see here, remember that we should meet two requirements to a set to be set as a partition of sample space. The first one is that there is no intersection between the event. Let's see here. For the set one, do we have intersection between A1, A2, A2, A3, and A1, A3? First, do we have intersection between A1, A and A2? Here,
No.
A1 is 1, 2, and A2, 3, 6. So we don't have an intersection here. And then between A2 and A3, also empty set. Yeah. And then between A1 and A3, also empty set. And then let's unify A1, A2, and A3. So the union between A1, A2, and A3 will form 1, 2, 3, 4, 5, and 6. So this form a sample space of tossing a die. So because the two requirements are met, then we can say that A1, A2, and A3 are the partition of sample space. But it is not applied to the set 2. Let's see here. In the set 2, let's see the intersection between B1 and B2, and then between B2 and B3, and then between B1 and B3. So, is there any intersection between B1 and B2?
3.
Yes, we have 3 here. Okay, and then between B2 and, oh, sorry, here also we have B4. So, yeah, we need to check one by one the intersection between B1, B2, B1, B3, B1, B4, and then between B2 and B3, B2 and B4, and then between B3 and B4. But if one of the pair between these B1, B2, B3, and B4 has an intersection, so the first requirement is not met. So we don't need to check the others. For example, here we have intersection between B1 and B2. B2, that is 3. So this means that the first requirement is not met. So because the first requirement is not met, even though when we unify B1, B2, B3, and B4, it will form a sample space, we cannot say this as a partition of sample space because not all requirements are met. So the set 2 is not a partition of sample space. Also, in the set 3 here, even though there is no intersection between C1, C2, and C2, C3, and C1, C3, but because the union between C1, C2, and C3 does not form a sample space, we have no 6 here. So it means that the set 3 is not a partition of sample space. Okay, so the right answer for this question is the set 1. Okay, So after we have learned about the set theory, now we will discuss about the probabilities defined on event. So because in our previous discussion, we talk about event, we talk about sample space, means that we talk about the member of these events that we defined. Now we will calculate the probability of our events. Okay, so what is the probability of the event? Yeah, so to calculate the probability of the event, let's say we have event A. So the probability of A, we notate that as PA. This is the ratio between the number of member of event A with the member of the sample space. So an A means the number of the member of event A, and NS means the number of the member of sample space. So for example, if let's say here, we want to calculate the probability of A1, so the value will be, the member of A1 is 2. So we have here NA1 divided by NS. So the number of the member of event A is 2 divided by the number of the sample space, that is 6. So we have 2 per 6, the probability of A1. Then the probability for B1, what do you think? What is the probability of B1? Our sample space here is here 1, 2, 3, 4, 5, 6. So what do you think the probability of B1?
3/6.
Yes, 3 over 6. 3 over 6. Because we have 3 number of member of B1 divided by the 6 member of sample space. Okay, so that's how to calculate the probability of an event. And now we will discuss about the properties or the condition of the probability. The first one is that the value of the probability should be between 0 and 1. Yeah, so we don't have any negative value for probability. Also, we don't have any value that is more than 1 for probability. And then, oh, I made a mistake here. I'm sorry. Here, this should be PS. So PS is the probability of the sample space. Yeah, this should be 1 because PS is NS divided by NS, and the value is 1. Okay. And then another condition is that for any sequence of event, let's say A1, A2, A3, etc., that are mutually exclusive, so we don't have any intersection between these events, or means that the intersection between AI and AJ, where I is not equal to J, is the empty set. So the probability of the union between all of these events will be equal to the sum of the probability of each event. So for example, if we have 2 events, let's say A1 and A2, then probability of A1 union with A2 will be equal to the probability of A1 plus the probability of A2. Again, if we have probability of A1 union A2 union with A3, and all of these events are mutually exclusive, means that they don't have any intersection. So this is equal to the probability of A1 plus the probability of A2 plus the probability of A3. Yeah, so we have this condition only if these events are mutually exclusive. So equation 4 is only applied when our events are mutually exclusive. Okay, here I have example. In a group of 500 women, 120 have played golf at least once. Suppose one of these 500 women is randomly selected. So we select one woman randomly. Then the question is, what is the probability that she has played golf at least once? So what do you think the value for this probability? What do you think the value for this probability? Yeah. So we can divide.
24%.
Yeah, sorry.
24%.
24%.
Yes.
Yeah, okay. So from where you get this number? Yeah, actually we can just divide 100. Let's say A define or represent the event that the woman played golf. So we will calculate this by divide an A with an S. So the number of A should be 120 and then divided by 500. So this will be, what is it?
0.24.
0.24, yes. So this is equal to 24%. Yeah. Okay. Yeah, I think the screen is rather delayed. Okay, so that's how we calculate the probability of event. Okay. Again, I have another example here. An urn contains 4 and then of them 18 are red and 22 are green. And then if one marble is randomly selected out of this urn, what is the probability that this marble is red? So we can just calculate PR. And then what is the probability that this randomly selected marble is green? So we can just write that as PG. So what is the probability that the taken marble is red? So this should be 18 over 40. Yeah. And then the probability,
0.25.
yes, okay. And then the probability that this will be green should be 22 over 40. Yeah, you can simplify this number. Yeah, using the decimal number or just fraction, that's okay. Okay. Now we have additional rules of probability. So here, just like the previous properties of the probability that I have explained to you, for example, if we have two events and these two events are mutually exclusive, so the probability of the union between these two events are just like the sum of the probability of the first event and the probability of the second event. So just sum these two probability only if the events are mutually exclusive. Yeah, but if these two events are not mutually exclusive, means that we have intersection between A and B. So the probability of the union between A and B will be equal to the probability of A sum with probability of B, and then we subtract that with the probability of the intersection. Yeah, so for example here, for two events that are not mutually exclusive, for example, let's say we roll a die once and then we have our sample space here is 1, 2, 3, 4, 5, and 6. And then I have A, event A as the appearance of the side that is less than 4. So we have 1, 2, 3. And then let's say B is the appearance of the odd numbers. So we have 1, 3, and 5. Okay. Now we can calculate the probability of A union with B, yeah, in two ways. The first way is that first we unify or we list the member of the union between A and B. So first we determine the union between A and B. So the union between A and B here should be 1, 2, 3, and 5. And then we calculate the probability of this union. So here we have the member of the union between A and B divided by the number of sample space. So we have here 4 over 6. Yeah, or 2 over 3. Okay, now this is the first way. The second way is we can use this formula. That is, we sum the probability of A and the probability of B, and then we subtract it with the probability of the intersection between A and B. Why do we subtract this with the probability of the intersection? Because let's see here, if we have Venn diagram for for event A and event B, and then here we have A intersect B, intersection between A and B. So the member of the intersection is calculated twice. Yeah, because it is the member of A and also the member of B. So if we only sum the probability of A and the probability of B, in fact, we calculate the probability of the intersection here twice. But we need only one, so we should subtract that with the probability of the intersection itself. Okay, so here, the probability of A is 3 per 6 because we have 3 members of A. And then also the probability of B is also 3 per 6 or because we have 3 members for B. And then we should determine the intersection between A and B first. So the intersection between A and B here is 1 and 3. So we have 2 over 6 probability of the intersection here, 2 over 6. So we have the result here also 4 over 6 or 2 over 3. Yeah, so we can calculate in two ways. The first way is, yeah, just list all of the member of the union between A and B first, and then calculate the probability. Or the second way, we can use this formula. We can use the formula number 6. So sum the probability of A and the probability of B, and then we subtract it with the probability of the intersection between A and B. Okay, so that's the additional rule of probability for general cases. And then we can also expand the formula in number 6 to be more than 2 events. For example, here, if you want to calculate the probability of the union between A, B, and C, so this will be equal to the sum of the probability of A, the probability of B, and then the probability of C, and then we should subtract this with the probability of the intersection between each pair of the events, and then we plus or we sum with the probability of the intersection between A, B, and C. In the geometrical representation, for example, here we have A, B, and C here. So we have A, B, and C. Let's say we have here the blue one is the intersection between A and B. And then the green one is the intersection between A and C. And then the black one here is the intersection between B and C. So, intuitively, when we want to calculate the probability of the union between A, B, and C, then we should sum all of the probability of A with probability of B with probability of C, but because each of the intersection is calculated twice, so we should subtract that once. So for example here, if we calculate the intersection between A and B, actually when we add the probability A and the probability B, then it it includes the probability of the intersection between A and B. So we should minus with probability of the intersection between A and B. And then when we sum the probability between A and C, yeah, so actually the probability of the intersection between A and C is also included in the summation, included twice. That is when calculate the probability of A and when we calculate the probability of C. So we need to subtract this with the probability of the intersection between A and C. Again, because when we sum the probability of B and C, actually the member of the intersection between B and C is calculated twice. Yeah, so we should subtract this with the probability of B intersect with C. Now here, let's see the yellow color here. So here, the yellow color here actually is the intersection between A, B, and C. Have we have subtract the probability of each intersection, and we subtract that what is it, twice, let's say. So when we subtract probability of A intersect with B and the probability of A intersect with 3, actually we what is it, we subtract the yellow color here. So we need to again calculate the probability of the intersection between A, B, and C. That's the intuitive explanation for this. But now we will prove this equation using a mathematical way. Yeah. First, let's assume that the probability of A union with B union with C can be written as the probability of A union with B, and then we union this union with C, like this. Yeah. So let's say we have like two types of event. Let's say the first event is the union between A and B, and then the second event is the event C. So using our first rule of the probability of the union, yeah, this rule here. So consider that A union with B here is just like the event A, and the event C is just like the event B here. So we can sum the probability of the first part of the union. So here we can sum the probability of the first part, that is the union between A and B, plus the probability of C, and then we will subtract with the probability of the intersection between A union B intersect with C. Okay, and then we will use the, let's just write this first. Then in the third part, we will use the what is it? We will use the law of the association in the distributive law. I mean, in the set theory, yeah, where if we have the union between two events and then we intersect that with the other event, so this will result the probability of the intersection between A and C, and then we make the union between the intersection between B and C, like this. Okay, again using the equation number 6, so we can break down the probability of A union B. So we have probability of A plus the probability of B minus the probability of the intersection between A and B, and then we plus here with probability of C, and then minus. So here, let's say we have like two new events, that is A intersection with C and B intersection with C, and then we will we will make union between these two. So using the same rule with equation 6, so we have here probability of A intersect C plus probability of B intersect C minus probability of A intersect C and then intersect with B intersect C. Okay, so we will gather the same kind of probability here. The first one is probability of A plus probability of B plus probability of C, and then minus probability of A intersect B minus probability of A intersect C minus probability of B intersect C, and then plus the probability of A intersect C intersect with B intersect C. So here we have probability of A plus probability of B plus probability of C minus probability of A intersect B minus probability of A intersect C, and then minus probability of B intersect C plus, so the intersection between A intersect C and B intersect C is equal to the probability of A intersect B and intersect C. So here we have proven the equation number 7. We can also expand this into the more than 3 events using the same concept. Okay. Yeah, that's the additional rule of probability. Let's see the example here. Consider a pack of 52 playing cards. A card is selected randomly. The question is, what is the probability that the card is either a heart or a 7? So yeah, we have note here. So 52 playing cards consist of 13 ranks in each of the 4 suits. So we have 4 seats that are clubs, diamonds, hearts, and spades. And then each seat includes 3 court cards, that is king, queen, and jack. And then each of suit also include 10 numeral card. That is 1. 1 is ace, and then up to 9. This should be 9. I'm sorry. 1 up to 10. Yeah. Yeah, that's true. 10. Okay, we don't play joker here. Okay, so if we have 52 playing cards, the question is, what is the probability that the card is either a heart or a 7? So what do you think here? First, let's define our event. Our event here, first, let's say A is the event of the appearance of a heart. Let's say a heart. Appearance. And then B is 7. A 7 appearance. Okay. So do we have intersection between these two events? Do we have intersection? Do we have heart number 7? In a playing card? Don't you know playing card? I think you already know what is 52 playing card. Hello, anyone? Do we have intersection between A and B? Yes, okay. Muhammad Adam. So what is the intersection between A and B? Yeah, I think the men should know about this card number 7. Card number 7 for what seats? Yes, card number 7 for with what seat? Yes, for heart. Yeah. So we have the intersection here is a heart number 7. Number 7. Okay. So the probability of A here is, yeah, what do you mean the probability of what is the probability of a heart appearance here? How many heart we have in this 52 playing cards? Ten heart? 10 only? 10 or 13? We also have king, queen, and jack for each seat, yeah. So it is also included. So we have 13. 13 over 52. Yeah. So we have a card with heart suite consists of 10 numbers and 3 court cards. So we have 13. 13 over 52. Okay. And then what is the probability of B here? How many 7 number we have from 52 cards? How many 7 numbers? Don't you have any description about the playing card? I think that should be any a description about this. So let's say we have we have club. Let's say C, and in this C we have 10 number cards and 3 court cards. Also in the diamond we have something like this, and then also in heart and also in spade we also have 10 number cards, and we have 3 court cards. Yeah, so we have 13 times 4 playing cards, so we have 52 playing cards. Okay, now again let's see, we have even A, that is the appearance of the heart. The heart here we have 10 and 3. 10 number cards and 3 chord cards. So we have 13 over 52. And then B is the event of the appearance of card number 7. In each seat, we have one card number 7. So if we have 4 seats, how many 7 we have? How many card number 7 we have? 4. Yes, we have 4. Yes, we have 4 over 52. Okay, so we have 4 over 52 for our event B, and then we have the probability of the intersection between A and B, because we have one hard number 7, so it will be 1 over 52. So the question is, what is the probability that the card is either a heart or a 7, or means the union? So the question is the probability A of the A union with B. So we will use the equation number 6. That is the probability of A sum with the probability of B, and then minus the probability of the intersection between A and B. Yeah. So here we have what is it? We have the value for each of the probability. Then we can just calculate. So the probability of A union with B is equal to the 13 over 52 plus 4 over 52, and then minus 1 over 52. Yeah. Then the result is 16 over 52. Yeah, so that's the result for this question. Okay. Yeah. Yeah, before I go to the next example, do you have any question up to this part? I think we only need 9 minutes left, Dr. Dorliana. Is it?
Yes, we have another 9 minutes. Okay. But we
Okay.
start very late.
Okay. Yeah. So, any questions up to this part, everyone? If there's no question, then I have question for you. Okay. My question is, let's say, the question is, what is the probability that the card is either a heart or any numbers besides 7? So my question is, what is the probability that the card is either a heart, just like before, or any number other than 7? So what do you think the answer for this? What do you think? So actually the question is, what is the probability of the union between A and B complement? Yeah, because we want to know the probability of that the card is either a heart or any number other than 7. So any number other than 7 means that we have B complement. So here again, we should determine the probability of B complement. The probability of B complement, it should be 1 minus probability of B. So we have 1 minus 4 over 52. Then we have what is it, 48 over 52 for probability of B complement. Another probability that we should calculate is the probability of the intersection between A and B complement. So what do you think? The intersection between a hard appearance and any number other than 7. The intersection between a hard appearance and a 7 appearance will be a hard number 7. But the intersection between a hard appearance and any number exclude 7 will be another 12, right? Will be another 12 card in hard. Is it? What do you think? What do you think the intersection between A and B complement? B complement is the number. So B complement is number excluded 7. Oh, not number, yeah, not only number, but card excluded 7. Yeah, we know that the probability of B complement will be 1 minus the probability of B. Yeah, so it should be 48 over 52. But the question is, what is the probability of the intersection between A and B complement? So the intersection between hard and any card other than 7. So this will be, what do you think? 12, yeah? Yeah, over 52. Yeah. So the probability of the union between A and B complement will be the probability of A. I will write in the upper part. So the probability of A union with B complement will be the probability of A plus probability of B complement minus the probability of A intersection with B complement. We know the probability of A is 13 over 52, and then probability of B complement is 48 over 52, minus the probability of the intersection between A and B complement is 12 over 52. Then the result will be 49 over 52. Yes, yeah, so like that. Yeah, so that's how we calculate the probability of event. Okay. Yeah, I think here maybe the last example from me. Actually I still have many many slides for this. I have 67 slides, but we can only discuss up to 25. That's okay, but I will share this slide to Dr. Nurliana so she can share the slides to you. Okay, so the last example. The following athletes are in a room. So there are 5 men with a height of 170 centimeter and over, and then 4 men with a height of under 170 centimeter, 6 women with a height of 170 centimeter and over, and 3 women with a height of under 170 centimeter. And then the following events are defined. Event A represent the athlete with a height of 170 centimeter and over. And then P is the event that represents the athlete with a height of under 100 centimeter, 70 centimeter. and then C is the athlete is male, and the D is the athlete is female. Then the question is, what is the probability of the union between B and D? Okay, so first maybe let's just gather the information first. So probability of A, what do you think? What is the probability of A? The athlete with a height of 170 centimeter and over. What is the probability? What do you think the probability of A here? The athlete with a height of 170 centimeter and over should include all of the male and the female athletes. So we have 5 men with this height and how many? And 6 women with this height. So we have 11 over the total number of the athlete. How many athletes we have here? 5 plus 4, 9, 9 plus 6, 15, and then plus 3. So we have 18. Yeah. Then the probability of P. What is the probability of P? The athlete with a height of under 170 centimeter. We have 4 men under this height, and we have 3 women under this height. So we have 7 over 18. And then the probability of C, that is the probability that the athlete is male. So we don't consider the height, we only consider the gender. So we have 9 male athletes. So here we have 9 per 18. And then the probability of T is the total number of female athletes here. So we have 6 and 3. So 9 over 18. Okay. Then to calculate the probability of the union between P and calculate the probability of P, sum the probability of D minus the probability of P intersect with D. Now this one we don't, this one probability of the intersection between P and D is the one that we don't have yet for now. So what do you think the probability of the intersection between P and D? The intersection between the athlete with a height of under 170 centimeter with the athlete is female. So the intersection should be the female athlete. Yes, 3 per 18. Yeah, the female athlete with the height under 170 centimeters. So this should be 3 over 18. So the result will be 7 over 18 and then plus 9 over 18 and then minus 3 over 18. So we have, how many is it? 13 over 18. Yeah, so we have this 30 over 18. Okay, now the question is, what is the probability of the complement of A intersect with the complement of C? So A complement means the athlete, what is it? Probably A complement. Probability of A complement. What is A complement? A is the athlete with a height of 170 centimeter and over. So the complement for this is just equal to B, right? Yeah, so this is just equal to probability of B. Yeah, so A complement is just equal to B, and then C complement, probability of C complement is just equal with D. Yeah, so probability of A complement intersect with C complement is equal to the probability of B intersect with D. Yeah. So yeah, this is the result is just like the probability of here. Yeah, the probability of the intersection between B and D. Okay, so that's how to calculate the probability. And before we calculate the probability, actually we need to understand some terms in the probability, just like set theory, like what we have discussed before. So we have experiment, sample space, and then what is it, event. And then we also discuss about the properties of events. So when we have two or more events, then we have some relation between these two or more events. And then also how to calculate the probability defined on event. So I think that's all from me. Actually, you can also learn about the conditional probability, and then the multiplication rule of probability, law of total probability, and also Bayes rule. And also the answer for our introduction before is 23. I will leave that for you. That's called as birthday paradox. So we can act, because actually to solve that we need the understanding about the conditional probability. So maybe Dr. Norliana or the other lecturer will explain to you later about um, how to solve this birthday paradox problem using the conditional probability. Yeah, I think that's all from me, Dr. Norliana. Thank you very much, and I do apologize for all my mistakes in delivering this material, and I will give the time back to you. Thank you very much.
All right, thank you, Dr. Dina. It's a great sharing sessions with a lot of example, yeah, in a real life, and I'm sure that student learn a lot today. Is it is it right, student? Okay, ka? Give a thumbs up to Dr. Atina. Okay, so they have
Thank
learned
you.
all, and we will the next part we will continue in our class next week. Okay, all right. So before we end our session, so let we have a photo. We will take picture first, right? So student, can you turn on your camera? So kita akan ada memory lah sikit dengan Dr. Atina today. Okay, turn on your camera. The attendance form I already share in the chat box. Okay, don't forget, make sure you fill in the form. Okay, everyone, please turn on your camera first. I want to take a picture.
I think they are too shy because there is no student to turn on the camera. That's okay, just like in here in our students, just like that, Dr. Nurliana.
I don't know what happened behind the scene of their camera. All right, my student Alice, Hanim, Nazhan, I call beberapa nama lah, Akil ke kalau ada. Okay. Ada on yang ada kat sini? Nurul Iman, Nurul Syuhada, Nuraina, Aisyah. Ada? Tak ada. Okay, turn on camera please. Okay. Okay,
Yeah,
thank
let's
you.
just take a
Akil.
photo.
Okay, Aisyah,
Everyone.
Anura, Asitina, Alisa. Okay, good. Okay, anyone else please? Kita nak ambil gambar dengan Dr. Atina. Nanti tak jumpa dah. Next year pula. Alright. So please everyone. Okay, boleh ke? Okay. Tak dah. Okay, no more? No more. Okay. So, okay. So 1, 2, 3. Alright. 1, 2, 3. Okay, last one. 1, 2, 3. Senyum. Okay. All right. All right. Thank you, everyone. Okay. Thank you, Dr. Adina, for today's session. We have learned a lot. I also revived back my knowledge in this topic. Okay. Okay. Puan Syafiza, Dr. Fida and Cik Karen ada nak share ataupun nak cakap apa-apa before we end the session?
Okay, thank you, Dr. Atina. Can maybe you share your slide with me?
Yeah, of course. I will share my slides.
Especially the one that you have written on.
Oh, yeah, okay.
Because there's lots of examples.
Yeah.
Okay, all right. Thank you so much, Dr. Atina.
Yeah, you're welcome, Dr. Afida,
Okay,
Dr.
we'll
Nurliana,
be in
and
contact
the others.
soon.
Yes, of course.
Okay.
And I also will wait for the photos from you.
All right, sure.
Yeah. Thank you very much, everyone.
Okay.
All right, thank you, everyone.
Have a nice weekend, everyone.
Yeah, have a nice weekend, everyone.
Assalamualaikum.
Waalaikumsalam.
Assalamualaikum. Terima kasih.